Okay, so in the last video we got the power wired up, and let's make sure our capacitors are 1 micro. And let's take a look at the datasheet again. Here we go. The AP2120, and these are 1 microfarad decoupling capacitors on each side, so make sure you get that. Next, let's add the power flags. So I will press the power symbol, and let's go with 5V, 5 volts, put it somewhere here. And let's add the 3.3 volt flag as well. 3.3 volts, there we go. In my schematics, I like to have the higher side be a little bit taller, so there's kind of a drop in voltage. It's your personal preference whether you want to do this or not, but I like to just keep it this way. Makes it a little bit more intuitive. Okay, so let's take a look at the not reset pin. If I go into the datasheet, NRST input characteristics, let's take a look. Page 65. It is connected to a permanent pull-up resistor. Our pull-up is roughly 40 kilo ohms. It can range between 25 to 55 kilo ohms, and it's permanently pulled up. So even if we leave this pin unconnected, it'll be pulled up. So what we're looking at now is to create some sort of mechanism where we can toggle whether this pin goes low or high. And I've been thinking about this for a little bit, and we have the reset here, and it comes from the ST32 here. And if we take a look at the schematic for the V2 link, we have T and RST here from our serial wire debug, and it goes into this pin here, PA7. So the ST link is going to toggle the not reset pin for us. So one scheme I've thought out for that is putting an NMOS. So open the parts symbol placer, just type in NMOS and we'll get one symbol here, and the NMOS will conduct from the drain to the source. I'll just go into the symbol editor, fix the grid, and I'll make the connections like so. And what our reset pin is going to do is it's going to connect to our gate. We're going to have to ground the source. So I will double click to cancel my wiring to finish the wire there, and then I will place the ground. I can remove this ground text here. If you click and you press M, it'll choose the move option, so you don't have to, sometimes it's hard to click and drag, or you can choose your own personal preference. So the good thing about this is going to be positive logic reset. It'll go to the gate here and it'll ground the not reset pin. So what's kind of happening is, let's draw this. You will have your 3.3 here, you will have your R pull-up, which was roughly 40 kilo ohms, and you'll have the transistor here, and we've connected this to ground. So when our reset pin here is high, this will begin to conduct, and this will ground this node, and there's a property of the transistor that'll turn it into a very weak resistor, which we'll just call R on. So when the transistor's on, we'll have some kind of resistance on there. Usually this is very low, typically in the milliohm range. We go to Desmos, and we take a look at a voltage divider. So that's 0.3, and let's just do 10 milliohms. What is that? 0.001, and then 40k plus 0.01. We'll get a very low number. We can even do this. This is tiny. So this will be practically 0 volts here. So this is one scheme I've thought out for the reset pin. And the good thing about this is we don't need a lot of components to create that inverted logic. So we'll have the reset, this will be high, and then this will pull down to low. One thing to keep in mind is that the gate will never discharge. So we might want to put a pull down resistor here, and perhaps even a capacitor, so that we do not trigger the not reset pin. A good value could be 1 micro, and just my instinct is going with 5k ohm pull down. Let's just take a look at the so you can think of there's a capacitor between the gate and the source here, which will charge up and it'll never discharge. Perhaps let's take a look at the V2 scheme and see if it does discharge. So perhaps it's grounded in the A7 pin, but we might not want to take a risk with that. So we could just add a 5 kilo ohms pull down resistor, edit the symbol. I'll just move these pins around, snap them onto my desired grid, and let's just wire it to ground. Let's move these reference designators a little bit nicer. There's a good place for them. 5k is the value we want. Copy, paste. So now when this is off, it'll discharge through here. You might be thinking, oh wow, isn't this going to consume power? And the answer is yes. When this is on, it'll consume power, but it shouldn't be anything bad. So this is the current that's going to go through. How many milliamps is that? It's not even a milliamp. So we can put a label here, less than 1 milliamp. So that's not a lot of current. We're not wasting, in comparison to the power in the MCU, this is completely fine. Okay. Is there a boot 0 pin? Let's see what we're going to do with the boot 0. Boot 0 pin is on PA14. Alright, but PA14 and 13 are our serial wire debug in and out pin and our clock pin. So we cannot ground PA14 in this case. So it has an alternate function, the serial wire, but we can make those connections right now. The serial wire clock goes to our clock up here, and our IO will go to our IO. Excellent. Okay. And let's add some LED functionality. So the LED that I found is the IN-S66TBT RGB. There's plenty of them in stock. It's an RGB type of LED. So it'll have, let's take a look at the data sheet. So it'll have 4 pins, 1, 2, 3, 4. One is the common anode, and the other 3 are the colors. So we have the red, green, and the blue. So let's actually find this part in KiCAD. So we add the symbol, and let's just search for RGB. It's important that the pinouts match here, so we need to be careful. We're looking for a common anode. That's good here. Let me make this a little bit smaller. Number 2 is red, so let's see, might be this one. 1, 2, yes, this is the symbol we're looking for. So for this particular LED, make sure you get the find a symbol that matches this particular pinout. And in our case, it's the, you can search for LED_ARBG and you'll find it. Okay, let's rotate it, put it down on the schematic. Okay, so we might want to give ourselves some more space here for the LEDs. So let me wire down right away, like so. Let's connect ourselves to the clock pin. Same thing with the IO. There we go. So now we have a little bit more space here. So one question we have is, do we drive this on the 3.3 or the 5 volts? So let's take a look at the forward voltage drop. So in the electrical characteristics data sheet, we see that the red is going to have a forward voltage drop of typically 2.2. So we could power this on the 3.3 volts rail, but the other colors, green and blue, have a typical voltage drop of 3.2 and even as high as 3.6, which is higher than 3.3. So we cannot run this on a 3.3 power rail, which means that we're going to need some kind of controlling circuit to trigger. We're going to have to run these on 5 volts, and we're going to have to control these on our pinouts here. So I've devised the scheme for that. So let's add some more NMOS transistors. We're going to need 1 for each color. So 1, copy, paste. We might even move this here like so, and let's connect the ends here to ground. So just copy this ground symbol, paste it. Okay, actually these NMOSs are not snapping onto the grid, so I will copy this one, which we did fix. And keep in mind that the NMOS will conduct from the drain to the source. Make sure you have the right orientation on these. And we can copy, paste. Great. And now we will select our GPIO pins and control the gates here, which will we'll power this from 5.5. Okay, we have to edit this symbol as well. Let me just move the pins around. There we go. Great. Snaps onto the grid. Save, exit. Let's move these ref deses out of the way. Great. We're also going to need current limiting resistor. So let's calculate these for each. Let me copy this one for now. Something like that. And let's go back to our whiteboard and let's draw out the we're starting with 5 volts. There's a voltage drop, there's a resistor, there's a transistor. So that'll look something like this. Voltage drop from 2.2 to as high as 3.2 typically through our current limiting resistor, and I'm going to assume that the transistor has been shorted. Okay, so now we're looking for the value of this resistor. Let's take a look at the data sheet and see what the typical, okay, I forward is 20 milliamps roughly. Right, so we need to, let's go back to the whiteboard. We need 20 milliamps to go through. So we'll do 5 volts minus, so for red, it'll be 5 minus 2.2 divided by R should equal 20 milliamps. So let's go to Desmos, and let's go 5 volts minus 2.2 divided by, so we can actually multiply this out right away, like so. So we divide by the current, 20 times 10 to the power of -3. So for the red color, we will need 140 ohms roughly to get around 20 milliamps. Okay, if we want to be on the safe side, I guess we can add a little bit more resistance here, but typically this should be okay. Let's do a calculation for 3.2. So for the red and green blue, so for the green and the blue colors, we will need 90 ohms here. Okay, so that's that for our current limiting resistors. Let's wire this up and let's connect the pin out. Let's do this pin. If you think this is messy wiring, you could use this label right here. You could type in red LED CTRL, set that equal to output, and you could press X to flip it, and you could connect this on the gate pin here, and another equivalent flag with the same name. Actually, let me cut that out and let me put that here. So this is actually the output. And let's put a flag input. It's gotta have the same name. We could put that here. Now this will look a little bit less messy, and you can even pull this out here, make it a little bit cleaner. It's the same thing as a wire, but I try to keep these labels, if they're on the same page, I try not to have these labels, because it can get a little bit confusing. So if the node is on the same sheet, I try to just wire it, and I try to use these labels for when a signal is going out into another sheet. But it's personal preference. You can choose whatever you want. Let's click save here so we don't lose our work. Let's be very clear with the labels, which one's which. So let's type out red here for this one. In fact, we could even name the node red. So let's do that. Add a net label. Press here. Let's do red LED CTRL. Okay, we'll put that. Now that we've named this node red LED control, let's do the same thing with the other ones. So this one's green, GRN, LED, CTRL. Let's put them underneath each other, and let's do the same thing for blue. Excellent. And this is going to help us later when we're routing and laying out the PCB, because these will then have names in the layout tool, which will help us tremendously, because they will otherwise just have default names. So let's actually do that here on these ones as well. SW clock for serial wire debug. To actually serial wire CLK. So it's important to name these nodes later. Let's press M and let's just move it back. There we go. Perfect. So these ones will label the nets automatically. So if we go to our routing tool, this will be 5 volts. This will be 3.3 volts. Here we could actually label this as RST, that here, and NRST here. Great. This will help us tremendously, and you'll see why when you begin routing. So that's our control for the LEDs. Great. We just added some functionality here. So we now have GPIOs that'll trigger the NMOS. It'll create a path to ground, and from our 5 volts we will run our LEDs with roughly 20 milliamps. Excellent. Honestly, for this little project, I think that's mostly it in terms of functionality. So let's cross out all the pins we will not need with a no connection flag. Okay, excellent. There's one thing we'll need for the microcontroller, and that's the coupling capacitors.